Okay, so let's get started today. We got a few topics today. First of all, I just want to review some of the most common problems I saw in Lab 2. Then want to show you a more efficient solution to the middle code problem than the one that you were programmed in lab yesterday. And finally, we're going to go and review classes today. We may or may not start into hash tables. I kind of doubt we're going to get to hash tables today. If we do, it will be just a quick overview before starting into it. Alan?
We did go over the middle code efficient solution.
Okay, with the, okay, so with the, and did you also go over the running times, the contrast between?
Loosely, yes.
Okay.
But
So.
people were committed by the math before it just yet.
Okay, sounds good. Okay, well, we'll probably do it a second time because I think it's important. One of the things about the class is making you think more carefully about how you solve problems and not just going with the first solution that comes to mind because it could be inefficient. First, I just want to quickly talk about a couple issues with Lab 2. Biggest issue I saw with Lab 2 is that many of you are too trusting of input data and not trying to think through all the possible ways that input might be erroneous. And two of the most common mistakes I saw in Lab 2 were, first of all, assuming that pixels would be numeric. So I saw a lot of code that checked to see whether the pixels were between 0 and 255, but trusting that the pixels would be numeric. But there's no guarantee that they would be numeric. The lab assignment write-up did not make any guarantees that the pixels were numeric. And in fact, I believe it was, I forget whether it was 58 or 68, which of those two test cases had a pixel called Thor buried deep in the PGM file. Not early on where you could easily see it, but deep in the PGM file it had a pixel named Thor. So many of you had issues with that particular PGM test. So you need it to, so what I was seeing was code that said while cin into pixel. And that was a clear indication that you thought the pixels would be numeric. And then when you got down here, you did some other stuff. But if the pixel wasn't numeric, then you got down into this other stuff, and sometimes you segfault it because the pixels had not been completely read. Sometimes you printed out the wrong error message. But it all came down to this naive assumption that the pixels were numeric. Okay, so you couldn't make that assumption. The second assumption I saw was one where you assumed that if we told you assuming there were enough pixels in the file. So if you were told that there were columns, number of pixels, and rows, that there were columns, that many columns and that many rows, you were assuming that there were that many pixels in the file, that we weren't going to cheat you on those pixels. Okay, so I saw a lot of you who calculated something like num pixels equals, and then a for loop that said for I equals 0, I less than num pixels, I plus plus, and cin into pixel. So again, the mistake here is, first of all, assuming that it's a numeric pixel, but the other mistake here was never testing to see whether the read succeeded. You just went ahead, and the next thing I saw in a lot of code was if pixel less than equals 0 or pixel greater than 255, I saw an error message. But this is making two critical assumptions here. It's assuming that the read into pixels succeeded. It's assuming the pixels are numeric, okay, and it's assuming there were enough pixels in the file. But that was the other test case. Either 58 or 68 did not have enough pixels in the file. So you need to get in the habit of not being trusting of input data. When we give you a lab, we will tell you what you can trust. If we don't say that you can trust something, then you need to assume it's not trustworthy and you need to check for it. And you need to get into the habit of trying to think about the ways in which data might not be trustworthy. You might say, well, you should tell us all the ways it might not be trustworthy. That's not, we did that in 102, but you have to start getting into the habit of doing it yourself. Because in the real world, someone's not going to do that, but hackers, you can be sure, are going to be looking for ways to give your code bad data that will allow it to hijack it and get into someone's program. Okay? Now, we've given you a lot of test cases, so if a test case fails, oftentimes it's because there was some bad data in it. And you can add cin statements that will try to determine what that bad data is. But you need to get in the habit of not being trusting of the data. Okay? The second issue, any questions about that before I go on? Yes.
So I had the first one.
Mm-hmm.
I had a hard time like inputting the data and checking at the same time if it was an integer.
Okay.
Brief way of explaining
Yes.
that?
Mm-hmm. So the question was kind of how do you input the pixel value, check whether it's an integer, probably also check to make sure you haven't gone, that the pixel actually was, that there were enough pixels. So the way I roughly did it in my code was I had a loop. So I did my, so I had code for checking header information. So the first four, for checking first four pieces of information, right? That was P2, the rows, columns, and 255. Okay, and then if that got through, I did say something like I had a variable num pixels. In fact, I think I was even, to make it clear, I think I called it expected num pixels so that it was clear that this was an expectation. Okay, and then I'm going to use pseudocode for I equals 0 to expected num pixels minus 1 because we do zero-based indexing. And I would try to, first of all, do the read. So if cin into pixel. So if it succeeded, it's a number, and I have the pixel. So I just did a pushback in this case. So I had a vector, and I just pushed back. So it was like, say, pgm dot pushback pixel. Okay, so that was the successful case. Okay, if it didn't succeed, then this was the else case. And there's two possible reasons why it failed. Okay, so two reasons for failure. Else could have failed due to EOF or pixel not being an integer. So those were the two possible failure cases in this case. So had to check them both. The first case to check is for EOF. Okay, you could actually do it. No, that is the right order because if the pixel is not an int, that could have been because it was due to EOF. So you really want to check the EOF first. So if cin.eof, okay, that meant you didn't have enough pixels. Okay, you ran out of pixels before you expected to. So print a not enough pixels error and exit. Okay, so that was the first case. The second case is that if it wasn't the EOF case, it had to now be, it wasn't an integer. Okay, and in that case, whoops, let me finish this. Else print a pixel not in 0 to 255 range message and exit. Okay. Now, when I ran, when I started hearing about the issue with those two test cases, I wasn't sure what the problem was with the PGM files just by doing a VI because the PGM file was enormous. So I actually wanted to see what that pixel is. That's how I figured out it was Thor. So for debugging purposes, I initially threw a cin.clear in here to clear the stream, and then I read that into a string and I printed it out. And that's how I figured out that the pixel was Thor. Okay, this wasn't necessary. This was just debugging statements that I threw into my own code to see what the issue was with the file. In fact, if you were printing out an error message, I actually think a better error message in that case would have been pixel Thor not in 0 to 255 range, so that you'd know exactly what that bad pixel was. Okay, and in fact, an error message like that probably would have alerted many of you to what the issue was with that particular file. But I think Dr. Plank wanted you really thinking about it, didn't want to make it super obvious what the error was. Okay, so does that make sense? Now, one thing I just realized I did wrong here. I can't assume that it's a good pixel. I actually need a test right there to see if the pixel is between 0 and 255. So I'll just say here, actually need to add a test to see if pixel between 0 and 255. So that would, if it wasn't, that would be another error message. Okay. Okay. Just like let me. Someone's trying to get that down. I'm just going to, for a moment. There. So other questions about that? Okay. So that kind of took care of both cases. Okay. So that was the big issue with this lab, and unless there's other questions, I'm going to move on. Okay, so the second thing I wanted to talk about was this middle code problem. And if you remember the kind of algorithm I gave you, eliminated one character at a time, and then it would concatenate two substrings together, so first half and second half. Okay? And so what was happening is it was eliminating one character at a time that it was adding to T, and it was subtracting one character at a time from S. So for example, if you started out with middle code, and here's T, so here's, actually let's do it like this. So S starts with middle code, and T starts like this. Okay, so what happened at step 1 was we took the middle value, and since it was even, we ended up comparing E and L, and we moved E over to T, and we formed S as the concatenation of MIDDL with code. Okay, so that was step 1. Then in step 2, so now that gave us MIDDL code, and that's an odd length string, so the next character to move was L, so L moved over here. And we end up concatenating mid with code. Okay? So actually at this point T is EL. Then it's again even. So we compare C and D, and we move C over here, so we get ELC, and we end up concatenating mid and ODE. Okay, and you can see the trend, which is that at step 1 we had 10 characters. At step 2 we ended up with a string that's 9 characters. At step 3 we had an 8-character string. Step 4, we have a 7-character string. And it's going to keep on like that until we get down to just 1 character. So at each step, we are going to be creating a string that is 1 character smaller, but nonetheless, the first string is going to take 10 characters to construct. The second one will take 9 characters, the third one 8. And that means the total amount of work is 10 characters plus 9 characters plus 8 plus 7 plus 6 plus 5 plus 4 ... plus 1. And I'm not going to go through the math. You may cover it in calculus. But it's going to be 10 times 10 plus 1 divided by 2, which is equal to 55. Okay, and in general, the amount of work with a string that is of length n, so if string is of length n, okay, you will create strings with a total length of n times n plus 1 divided by 2, because that's what that sequence evaluates to, is n times n plus 1 divided by 2, which is n squared. And that number gets big fast. If we had a string that was 100 characters big, then we're looking at 100 times 100, or 10,000. Divide that by 2, and we're still looking at 5,000. It's not a small number. If we're 1,000 character string, so just looking at this for a moment, some string lengths, so n times n plus 1 over 2, and I'm just going to have approximate values here. So if n is 10, we're approximately looking at 55. If it's 100, we're roughly looking at 5,500 here. If it's 1,000, we're up to 550,000. If it's 10,000 in length, we're going to be up to 55, and we're adding 2 more zeros. we're going to be up to 5.5 million. Whoops, 55 million. So these numbers explode pretty quickly. And it's going to slow down your computer considerably. So it's worth thinking about if there's a more efficient solution to that problem. And there was. If you kind of did it out by hand, like I was doing here, what you would discover is that if you had an even length string, the next two characters to move over were always the middle two characters, if it was even. So no matter which of the two characters moved, at the next step the other character moved. And the reason is that the string's length decreased by 1, so it became odd, and whichever character was the loser became the middle element, and therefore it moved. Okay? So therefore, you could come up with a more efficient algorithm where you said, okay, if the string is even, then compare the two middle elements okay, add smaller element to T, add larger element to T. And now, is the string even or odd once we do this? If the string was even, we move 2 elements to T. It's even, guaranteed to be even. So basically, we can, now we realize that instead of just saying if string is even, we can kind of say while we know the string is even, we'll get to the odd case in a moment, but as soon as the string is even, it will stay even. So we can then just say while the length of the string is greater than 0, we'll compare the middle two elements, add the smaller element to T, and add the larger element to T. Okay? You say, okay, well, what about that case where it's odd? Okay, what do we do? Sarah?
What you can do is you can put an if statement above the wall and say
That's right.
if odd, then
Move the
add the element, and once you remove the element, then it's even.
Very good. So right up here, we just add something that says if string is odd, move middle element to T, and now the string is even and will remain even the rest of the way. Okay, I always found it amusing, perhaps it was on certain things near water, it gives 2 different instructions for how to save someone who's drowning. One if the person who's drowning is conscious, and one if they're unconscious. And it says if they're unconscious, just go out and kind of shoulder them up and bring them back. And the other one says if they're conscious, well, now it's really dangerous because they may try to bring you down with them. So try to avoid getting entangled with them, kind of then haul them to the shore. And some wag, maybe a lifeguard, had written, if conscious, knock unconscious. Follow instructions for unconscious. Okay, so that's kind of the idea here. If even, do all this stuff. If odd, make it even, then do the stuff for the even. Okay, so that's what we're doing. And then the other thing that you can the other trick that you can utilize, and you might say, well, how would I think of this stuff? And the answer is you won't necessarily think of it. That's why we tell you this stuff, because you get to add it to your bag of tricks. And when you've seen these tricks often enough, you start to think, oh, maybe that's a trick I can employ in this case. So I wouldn't necessarily think that you would think of this trick on your own. That's why I'm showing it to you. Okay, so this is an even length string, and I say, okay, what I'm going to do is I'm going to look at the two middle elements. That's L and E. So I'm just going to call this one the lower element and this one the upper element. Okay, so once I've deleted L and E, what are the next two characters I'm going to consider? D and C. The next two characters are D and C. Okay? Well, how can I get to the position, the D position from the L position? If I have the value 4 and lower, what do I have to do to lower? Subtract 1. Very good, Gerald. So I just subtract 1 from lower. And what do I do to upper? Add 1. So upper becomes upper plus 1. So instead of creating an entirely new string for S, which is what we were doing before, all we have to do is keep two indices, one called lower and one called upper. And at each step after we've moved the two elements, we just subtract 1 from lower and add 1 to upper. Okay, so back here, whoops, not back here. Actually here, so add smaller element to T, add larger element to T. So we can now kind of refine that. Okay, so basically we say if S of lower is less than S of upper, okay, move, and I have to get rid of the rest of this. So move S of lower to T, move S of upper to T, else it's the opposite. We move S upper to T, and we move S lower to T. And then regardless, we decrement lower and we increment upper. And now we have to change our stopping condition because we're not deleting characters from our string anymore. So its length is going to remain constant, but what test might now tell us that we've reached the end of the string? What test for lower?
No.
So lower won't become null, but it will. At what point would it become kind of not right to use lower anymore? Less than 0. So once lower becomes less than 0, we've moved off the end of the string. So we can replace this condition. Instead of saying while it is that, we can say while lower is greater than or equal to 0. Okay, so that becomes our algorithm. And this is a lot more efficient. We never created new strings. And if you think about it, we only looked at each character once. So if there's n characters, we only looked at each character once. We had, in effect, we only considered n characters rather than n squared. Okay, that's a huge improvement. Okay? Has everyone got this down? Okay, so n is a lot, as you can see here, n is a lot smaller than n squared. If you looked at the two graphs, it would look something like that, okay, with this being n squared and this being n. So you definitely want to try to come up with the most efficient algorithm that you can. And that's something we want you to start thinking about in this course, is how to do that. And we will show you these tricks as the course progresses to show you kind of how to sometimes think about things so that perhaps you can come up with an algorithm that is more efficient than the initial obvious brute force algorithm. Now, a corollary of that is if n is never going to be big, like in this particular problem, topcoder guaranteed that the size of the string would never be greater than 50, there's no reason to think about a more efficient algorithm. The brute force algorithm is fine. But in the real world, where you might be dealing with a very large number of characters or a large number of input elements, sometimes you have to try to come up with the most efficient algorithm you can. Okay? So any questions about this problem? Okay. Time to take a deep breath because we're going to now move into the last topic that is a review topic. And then starting on Tuesday, we'll be moving into new material involving hash tables. And from there on, it's all pretty much new material in this course. Okay, so the last thing, we went over it for a couple weeks at the end of 102, are classes. Okay, so do you remember from 102 what kind of data are classes used to store? What? Speak up, Senior. I can't.
Protected, like you want to protect the data.
Okay, that's right. You want to protect the data, but I guess I'm more kind of what kind? Like, what's the difference between the data stored in an array and a class? Still not quite there. Doug, okay.
It doesn't have to be the same type of data.
Doesn't have to be the same type of data. So classes store heterogeneous data. Is that going to be your answer too? So if like you have a driver's license and you want to store that information, you might have a name, you might have a zip code, which is an integer, you might have a birth date, that's a series of integers, you might have a street address, that's a string. So you need to store a collection of information. So Dr. Planck came up with a nice lecture. In fact, also reviewing, if you remember, when you declared a class, let's say it was driver's license, as Senior was saying, there typically were two parts. There was a protected part and there was a public part, right? And as Senior was saying, the protected part was your data. And what was the public part? Jeremy, your functions. So these were functions. You will hear them referred to as methods. They're synonyms. Okay? So functions are methods that manipulate the data. Okay? I don't have my roster here, so I'm just going to pick on someone. Stephen. Why did we make the data protected?
So the user can't change it.
That's right. So we don't want the user being able to come in and change it under our noses. We basically want to control access. It's like having a security gate and making sure that we control who comes in and out. So we don't want someone to change the data under our noses without our knowing about it. We want to control access, and that's how we do it, is through bringing is through functions, and people have to call functions in order to control access. Okay, so that's kind of leads us into Dr. Planck's problem. Okay, so he likes to learn the names of his classes, which I do too, but he has a different technique. So he'd take pictures, and then he would associate names with pictures and lay them out in a nice matrix like this. And actually, let's see if he has it, to help him memorize them, whoops, I don't have that. I guess it was too much. He would randomize the pictures, so they would appear in random order, and he could either have the names appear, or he could have the names not appear. So when he was first learning the names, he'd want to associate names with pictures. Later, to test himself, he wouldn't print out the names, and he would just try to guess. So these are different things. I believe this is his dog Harvey. And he, as you can see, Dr. Planck definitely, I like his sense of humor, you may not, but poor Taylor Swift ends up as Taylor Toxin. So this is, as I say, Dr. Planck's humor. Also, Dr. Planck likes rugby. That's why you see the rugby player. Not sure what all the other ones are. This is probably, does anyone know who this person actually is? I'm guessing a rock star. Pardon? Mick Jagger. So he's also a fan of rock, and that's showing how I am not. Okay. So at any rate, he does this. So he walks us through a program where he's going to create an HTML page that represents this. So we don't want to make this into an HTML lecture, so I'll suffice it to say that this uses an HTML table, and it's organizing the entries into rows, and you can see that there are how many entries per row? Per row? 6. Okay, so this should interest you because in Lab 3, you are being asked to print out your PGM files in columns of 20. So you might suspect that this particular lecture has a clue as to how to do part of Lab 3. Okay, so what's going to happen is we're going to assume that, so assumptions, and assumption 1 is 2 files. Okay, file 1 has names. So there's a name file, just a list of names, like say Brad VZ, Taylor Toxin, ... So list of names. Second is a picture file. Okay, it has JPEGs. And if I remember correctly, it's the name of JPEG. Let's make sure about that, but I'm pretty sure it's the name of JPEG files. It's no. In fact, we don't assume we have a second file, so we assume our second set of files are picture files, so there's multiple ones. But they have a certain encoding to them. So they all start with 00, and then it has 1001, 1002. So they start with 00, and then the first name is in 1001, the second name is in 1002, the third name is in 1003, and so on, JPG. So the first two identifying characters are 00. So 001 would be identified with Brad VZ, 0102 with Taylor Toxin. So the numbering of the files corresponds to the order in which the names appear in the name file. Okay, so what we want to do is read in these names and then associate a picture with each of those names. And we also want to lay them out in a table such that each row has 6 names in it. So that's the challenge we face. Okay? How does Dr. Planck suggest that we go about this? What form of programming? Does he think we should tackle the whole thing at once and write a 200-line program? No. What word does he use? And what word did we use in 102 to encourage you to do for programming? Pardon? Go ahead. No, not string stream. So this is a strategic way of programming. Incremental. We want you to do it incrementally. So do a little bit, test it, then do some more, test it. I know that many of you disregard it, but we're going to keep hammering it at you because it really is one of the biggest ways to decrease the amount of time you spend programming. Because if you do a little bit and you get it right, then the next little bit you add, if it's wrong, you only have to check the little bit that you added. Rather than it's wrong and now it's, think of a search area, okay? Let's say a body's gone missing, okay? And I tell you that it is in the area of Knoxville, okay? You have to find it. Versus I tell you that it is in my backyard. Okay, which do you think is going to lead to the faster find? Finding it in my backyard or finding it in Knoxville? Surely we have an opinion on that. Man in orange. Backyard. Smaller area, right? Okay, it's the same thing when you're debugging your program. Now we're looking for a bug. Okay? If you're looking for it in 200 lines of code, you're not going to find it as quickly as if you're looking for it in 10 lines of code. Well, that's what incremental programming does for you, is it narrows your search space. Okay? So intuitively, a lot of your time is spent debugging. Okay? A lot of my time is spent debugging. So I want to minimize that time. Well, if I have a smaller search space, that's going to reduce the time for me to find that bug. That's what incremental program development does for you. Okay? That's why we keep hammering on it. So Dr. Planck broke his problem into a number of steps. He said, okay, first of all, we are going to, just print out the names. Okay, so his first step, step 1, is simply read name file and print it. That was step 1. Okay, in fact, I'm going to move that to my notebook. So his first step, hello. That doesn't work, of course. Using this pen on my laptop, not a bright idea. Okay, step 1, print or read and print name file. And don't try to format it, just read and print name file. Okay, so that's pretty simple, but it gets the program underway and we feel like we're making some progress. Okay, so the next thing is we turn the names into HTML. Okay, I'm not going to spend a lot of time on that. I'll let you read up on it. HTML is a markup language, so You use markup. You use tags like table, tr to indicate the end of beginning of a row. Okay. The slash tr indicates the end of a row. The tag td signals the beginning of a new column. Within a row, the tag slash td indicates the end of a column within a row. So basically, we have to create these tags, and we also want to make sure that we put them 6 per row. Okay, so that's our second step, is that we're going to format names into an HTML table with, and I'll just say n names per row, because we don't want to hard code 6, we want to make it flexible. So we're not going to hard code it. So we're going to format the names into an HTML table with n names per row. Then, after we're done doing that, we are going to, come on, okay, we're going to add the image tags. So we are going to add the actual pictures to the program. So our fourth step is to add the images. Okay, so whoops, step 3. Sorry, step 3, add images and option to suppress names, because we want to be able to only print the images. So that's step 4. And step 4 is to randomize the names, because we want to be able to, you know how it is, I might have a seating chart make you all sit in the same place. It's easy for me to then identify you from the seating chart, but to really be able to identify you, I'd let you sit anywhere. But that would make it harder. So randomizing it really makes it so you can understand or make sure you've memorized the names and faces. So randomize the position of the names, or the photos. I'll say of the photos. Okay, so he breaks it into those 4 steps. And along the way, he has introduces some concepts that you may or may not have seen before, which is also important. Okay? So, the first thing he does is he's going to use a class. I'll actually admit this isn't necessarily requiring that. This isn't the best use of a class, but it certainly is a nice problem, and so we are going to do it using a class. So we could say, for example, that we're teaching multiple classes, or we're doing this for the university so that any professor could use this program, in which case we have a separate roster for each course. And so we're going to create a class called roster, and it's just going to have, as its one piece of data, a vector of names. So that's the names we're going to read from our file. And then we're going to have 2 functions for manipulating those names. One is a function that will allow us to add a name to the vector, and the other is our print function, which is going to print these names into an HTML table, as well as printing the photos. So this is a pretty simple class declaration. But he does something unusual with it. For someone who read the notes, what did he do? Where did he put it? Did he put it into the file where he put main? Did he put this class declaration into the same file as main?
Put it into a header file.
He put it into a header file. Very good, Gerald. So he put it in, he didn't, for the first time, we're looking at a program where it's not all in one file. Up to now in 102 and in 140, we put everything in one file. Well, in the real world, that's not practical. If you're Amazon and you have several million lines of code, it's not feasible to put the entire program in one file. Okay? There are a whole bunch of issues, one of which is you have multiple programmers. They have to be able to work independently. So you want to divide the program into multiple files so they can all work independently of it. Okay? There are other reasons. We'll get to them. But the fundamental point he's making here is we're introducing a new concept called header files. Okay? So a header file contains declarations. Contains declarations. Okay, as an example, one big thing they contain are class declarations. Okay, and they end with, by convention, .h. They have a .h suffix. That's how you know a file. You look at it, if you see .h, you know it's a header file. What is the advantage of a header file? Well, you can include that file in another file. Okay, you've been doing that in every program since 102. You include IO stream, you include vector, you include string, you include string. Those are header files. Okay, they don't have .h. That's because system files don't, C++ header files that are provided by the implementation don't have .h. That's how you know whether it's a system-provided header file or a programmer-provided header file. If it has .h, it's a programmer-provided header file. If it doesn't have .h, it was provided by the system. So, with this, you can include this header file in multiple files. Let's say this was Amazon. Well, yeah, let's say this was Amazon and we needed to include this class, this identical class declaration in 1,000 different files. It'd be pretty hairy if I had to change the class declaration. I'd have to change it in 1,000 different places if I put that same class declaration in 1,000 different files. And I might have a typo. So how do I get around that? Some clever person said, hey, why don't I declare it in one place in a separate file, and then I could simply include that file in my 1,000 other files. And that way, if I need to change it, I only have to change it in one place, and I avoid this issue with typos and inconsistency. So that's the advantage of header files. So pretty much starting from Lab 4, you're going to be putting your class declarations into header files. Okay, so that's the first big change. We still do not want you to put the function definitions in your class declaration. In fact, that will be very important now that you not put your function definitions into the class files. I'll explain why in a little while. So the class definition, the function definitions are going to go in a separate file. And typically, they do not go into main. Why? Again, think back to Amazon. We have 1,000 files. Why would we put all of our class functions into the one file with main? Again, it would defeat the purpose of allowing multiple programmers to work on our system. So typically, if we have a header file named roster.h, and that has our class declaration for roster, we will have a .cpp file with the same name that contains the function definitions for roster. So we are going to typically have a .h file for each class, and then for each .h file we're going to have a .cpp file that contains the function definitions for that class. So this is really something about project management. It's a project management technique to help us handle large projects. So you need to start getting into the habit of putting your class declarations into a .h file and then your function definitions for that class into a comparable .cpp file. And these files will be different than the file that contains main. Okay, so you may be thinking, okay, how do we tie that together? Okay, we have now, it looks like 3 different files. We have a .h file, maybe named roster.h. We have a file that contains the function definitions. And then we actually may have some other file, I'll just maybe for the time call it main.cpp, that contains the actual code for reading the name file, creating an instance of this class, basically gluing everything together. Okay, so we have 3 files, and Dr. Plank has a nice picture. Okay, so here's kind of the relationship. So in this case, he named them roster1, roster2, roster3.h because he had his incremental programming. So these are representing the steps. So roster1.h contains the definition of the roster class. Roster1.cpp contains the function definitions. Remember, method and function are synonyms. And then roster1 main.cpp defines the main procedure. It uses the roster class. Okay? Now, both of the .cpp files must use an include statement to include the .h file. And does anyone notice a difference between the syntax for this include statement and the one that we use for a system provided one? It's using quotes, okay? Rather than what? Rather than the thingy, the inequality brackets. So that's another, that tells, the quotes tells the compiler that this is a programmer included file, whereas the brackets tell the compiler that it's a system provided header file. If it is the system provided header file, the compiler has a predefined set of directories it looks in for those header files. If you use quotes, it looks in the current directory for the header file. Yes?
So is it just like by convention that you use .h? Because like,
Yes. I could use anything. I could use .bvz and be vain about it.
Or, well, like whenever I include something that I don't include like really often, like a math library.
Mhm.
If you look up stuff on the internet, there's like math, there's like C math, and there's like math.h.
So here's the deal. In the old C language, they didn't, all the system include files were also .h. And when it went over to C++, the developers of C++, I think, decided that's a little confusing, so we're going to make all of our include files not be .h. So when you see, yeah, you will sometimes see # include, I'm kind of gritting my teeth as I do it, like standard.io.h. And what's actually happening with that, that is a system file. So the absolute determinant of whether it's a system provided header file or a programmer provided header file is whether it's in quotes or braces. When you see a .h as a system provided one, you know that it's a old, I'll call it old C header file rather than the newer C++ header files. That's what you're getting into. Yes, Alan?
But I think it's worth pointing out, if I'm correct in saying this, that in every case, all they did was take off the .h and put a C in front, and that's the correct, proper way to.
Right. So then, eventually, yes. So eventually, they thought this is confusion. It's no good to mix these, and so instead of including standard io.h, they took the standard C libraries. They stuck a C in front of them. Okay, so instead of including standard io.h, you really are supposed to include in C++ C standard io. And I don't know about C programs, Alan, since I don't C program anymore. If it's still in C. Okay. So at any rate, in C++, they eventually said, okay, if it's an old C header file, we want to kind of get away completely from these .h system provided ones, so they just took the old C header files, stuck a C in front of them, and got rid of the .h. Okay, so that's why when you look on the thing and you see math.h and you see cmath, they're actually the identical one, except this is supposed to be the one that you use for C++, and this is supposed to be the one that you use for C. Okay, and there is sometimes slight differences between them. So you really, if you're using C++, want to include cmath, and if you're using C, you want to use math.h. Okay. Okay. So, but the bottom line is, if you want to use a .h file, you have to include it, and you do it in your list of include statements. Typically, put your system provided include statements first, and then your user provided ones, because your user provided ones often depend or may depend on the system provided ones. So put the system provided ones first. Now the next thing that has to happen is that we have to, the .h file is not a compilable file really. You don't really compile it. Instead, you're just going to compile the .cpp files. Okay, so you're going to compile the .cpp files, and then you somehow have to combine them into a single executable. Whoops. Okay, and that is called separate compilation. And here you see it in action. So it's just like what you've seen before. The -o flag names the executable, and then it's just a list in any order of the files comprising your program. So instead of listing one .cpp file, you now list all of the .cpp files. Okay, and you can see at the bottom, right down here, he says this is known as separate compilation. Because what actually happens is the compiler, even though you do three, as this is shown as one step, the compiler does this at 3 steps. It compiles roster 01.cpp, then it compiles roster 01 main.cpp. And if you were now to do an ls, you would see on your computer a file called roster01.o and a file called roster01 main.o. These .o files are called object files. They contain machine language or object code. Okay, object code, which is also machine language. Okay? So you now have these 2 separate .o files, and the third stage is it links the two files, the 2.0 files, into an executable named roster. Okay, and the link step, what it's doing is if you roster main or roster1 main contains some undefined functions. Okay, it has a call to probably print and a call to add name. Remember, those were the functions associated with the roster class. But those functions were not defined in roster1 main. So what the linker does is, or the compiler in each file keeps a list of, it keeps two lists. Okay, functions I define, and a second list, undefined functions. And what it does, the linker then goes through the list of undefined functions, and it consults every other file and looks at its functions I defined list. So the main, roster01 main, has for its list of undefined functions roster : print and roster : add name. And roster01 has as functions I defined those very two functions, print and roster : add name. So what happens is the linker in going through roster01 says, great, those two functions are defined here. I now know what these two functions refer to, and it adds jump statements to the code. So what it does, it takes the two object files and jams them together. So these are the 2.0 files, and it jams them together. Okay, and then so this is roster, say, 01 main, and this is roster1, 01. So there are some calls from roster01 main into roster01. Okay, some jumps into the code for roster01, where it defines the print and add name. So the linker is resolving undefined function names. Okay, is that clear? So separate compilation involves two steps. Okay, separate compilation has two steps. One is compilation of files, and two is linking .o files into an executable. And it has the advantage that if you change one file, you only have to recompile that one file. The other file, its .o file, is still up to date. So separate compilation saves you time. Imagine, again, Amazon. It has not just 1 million lines of code, it has several million lines of code spread over thousands of files. If you made one change and had to recompile the entire system, it might take hours, even on today's super fast machines. So you make one change and now you wait several hours before you get to test it. That's a drag. But with separate compilation, you only recompile the one file you changed, and then you run the linker. And the linker runs much more quickly than the compiler. The linking is very fast. It's just going through these lists of undefined files. So linking is very fast relative to compiling. So separate compilation on big projects saves us a lot of time. Okay, now, I said that it's super important not to put your function definitions into a .h file. Okay, why is it super important? You might be able to reason it out now. Let's say I had two files, file1.cpp and file2.cpp. Okay, and let's say that I had roster.h. And in roster.h, I was foolish enough to put the function definitions for print and add name. So I put the function definitions into roster.h, and then in both file1.cpp and in file2, I included roster.h. So both of them have the include statement. Okay, so what happens? File 1 comes up with the list of functions I defined. Okay, well, because it included roster.h, it has the code for roster print and roster add name. So these are two functions I defined. Well, file 2 gets compiled, and it has a list, functions I defined. Well, it has the include file 2, so it also claims to have defined roster print and roster name. Add name. Okay, the linker now tries to combine these two files. And it says, whoa, wait a minute. Both of you claim that you defined these functions. That's a no-no. You can't both define it. I only allow one definition of that file. And you might say, silly linker, they're the same definitions. Replace silly with stupid linker. The linker doesn't know that these two definitions are the same. It doesn't bother to go in and look at it. It just looks at them and says, I'll bet they're different. They're conflicting definitions. And it prints out a message saying multiply defined functions. Okay? Give me 1 second to show you the error message because you're going to see it and it's going to confuse you, but at least you'll have seen it once before that happens. So I'm going to do foo.h, and I am just going to put one function into it. I'm going to have int add, and I'm just going to have it return 3. Just a very simple function. Okay? Now I'm going to define file1.cpp and have it include foo.h, and I'll make it be main, and it is going to call add. Okay, and I also have it call another function bvz. So that's all it's going to do, and then I'm going to have file 1. Whoops. I want that to be file 1. So I'll have file 2.cpp define bvz. So int bvz, I'll have it return 8. Okay, very simple. Whoops, also have to have it include foo.h. So now I'm going to do my compilation. Undeclared identifier. Shoot. put that into my file too. So int bbz. So we'll talk about this, but this is putting the function prototype into there. Do the compilation. There it is. Okay? Duplicate symbol, LD. So hold on for a second. This is important. LD. See, duplicate symbol. It has some very obscure, unrecognizable stuff in two different .o files. Again, totally obscure. LD. LD stands for loader. Okay? And then clang. Error linker command failed with exit code 1. Use V to see invocation. So you know that there is some kind of multiply defined symbol. We will go over how to find that multiply defined symbol on Tuesday. We'll also get into hash tables on Tuesday.